Okay, hi everyone. Welcome back to another Breaking Into Data session. For those of you who don't know me, I'm Aaron Fallouse, founder and CEO of Promotable, and your host for tonight's session. With me tonight, I have my co-host, Julia Myers, and then our guest speaker, Giacomo Vianello. So really great background. He's a lead data scientist at Cape Analytics, and he is also one of the instructors on a Udacity course as well on DevOps and what we're talking about tonight. So if anyone's interested, the link is in the link description. I'll also drop that into the chat. Before we dive into it, just a quick reminder, definitely throw your questions into the chat. And as soon as we're ready, we'll answer all your questions. So definitely get those in. This talk is going to be recorded. It'll be on our YouTube channel as well. So with that, breaking into data, what is it? Who are we? Really, we are a community where accomplished data experts and professionals share stories, industry knowledge, and advice to inspire the next generation of data talent. So with that, let me hand it off to Giacomo, and then I'm going to share your screen and kick it off.
Thank you for having me. I'm glad to be here and to talk to you about MLOps. And this is going to be machine learning operations, MLOps, from the perspective of a data scientist. And so let me just start with a very short introduction about myself. So as Aaron said, I'm right now a data science lead at Cape Analytics. Cape Analytics is a startup in Silicon Valley that applies computer vision and classical machine learning to the insurance and the real estate industries. And before joining Cape, I did a bootcamp. So I was probably in the shoes of many of the people who are attending this call. I did a bootcamp that is called Inside Data Science here in the San Francisco Bay Area. And before then, I was at Stanford University. I was a researcher there for almost 10 years. I was doing machine learning applied to astrophysical data. So I always joke that back then my satellites were pointing up and now they are pointing down. But the work is actually much more similar than I anticipated. I'm also teaching on Udacity. I have already out a class that is part of the machine learning operations nano degree. And now I'm working on a class that is going to be part of the deep learning nano degree. I'm also on the side a consultant. I do phone calls and other meetings with people who are interested in knowing about the industry of machine learning and machine learning in general. So again, thank you for having me, and let's jump into the topic. So when you come from a background and you're just studying data science, and maybe you're doing some Kaggle competitions, and maybe you are following papers, academic papers about machine learning. The process that you see in kind of the machine learning space is kind of like this that I outlined here. So you start from a data set that is given to you. You do some exploratory data analysis where you look for missing data, or if you're dealing with images, try to understand what the images are and just try to understand a little bit the lay of the land. And then you start creating your model, and you go back and forth, kind of exploring the data set and creating a model until you get to a performance, to a metric of interest that is interesting, so that it matches, maybe the state of the art if you are doing academics, or maybe the leaderboard in Kaggle. And that's kind of the normal workflow there. And so on the right, that may be a typical allocation of time in a project like this. So you have 0% on data creation because the data is given to you. And then you have around maybe 30% of the data of the time in data exploration and cleaning. And then you spend the bulk of your time in modeling and maybe a little bit in the inference part. And so that's kind of the normal type of time allocation in this case. However, the production case is pretty different. Applying machine learning industry is pretty different, and I try to summarize it here in this kind of meme to summarize that the fact that you can solve a problem with AI on your laptop or on a cloud machine does not mean at all that you can actually build a reliable product around it and that you can put it into production. And so what we're going to talk about today is this process. How do you go from a prototype to a real product. Okay, so the first rule, of course, is that you need to focus from the beginning on production. And so in particular, whatever you train, whatever you build, must be deployable, which means that you have to have an artifact, something that you can actually deploy and that people can actually use for something. And in particular, a model is 100% useless unless you can put it in production for the organization that you're working for. And then a similar point, but also a little bit different, is that this model that you are building must be usable in your specific product. So, for example, if you can build a model that is only 70% accurate, but can be used in your production environment because it respects the constraints that you have there, using this model is infinitely better than using a model that is maybe much more accurate, maybe 90% accurate, but cannot be used. And so you have to think about what is available in your production environment and what are the constraints in your production environment from the beginning, because otherwise you will build something that then you cannot use. And then you want your model to be dependable. When you use your model in production, your model is going to see a lot more things that you anticipate. And so in particular, you will see corner cases that you didn't anticipate. You might see null values where you didn't have them in the training set. There could be performance drift due to data drift and these kind of things. And so you have to think about these things to make your model dependable. You also want your model to be explainable. In many industries, this is a requirement. And this can be done either intrinsically, you use an intrinsically explainable model, like, I don't know, linear regression or a tree-based model, or you can use explainability techniques like sharp values, saliency maps, and other techniques like that, depending on the type of model that you have. And then finally, when you are building something for real, you want this something to be reproducible. You want somebody else to come and be able to reproduce what you did. This somebody else could be yourself in a year from now, or somebody else from the same company, the same organization. And so essentially a realistic workflow, even though it's pretty simplified, could look like this. So, So you start from a customer expert. It can be yourself or can be somebody else in your company or organization. And you try to define a product, right? You're trying to define what you want to build. And this is an iterative kind of exercise. You go back and forth until you focus on a certain idea. And then once you think you have something that is compelling, you start collecting the data for it. And then you also need quality assurance on the data to make sure that the data is good. And so this is the data collection part. Then you move to the model training part and the model evaluation, where you train your model. And sometimes, and actually often, in this kind of situation, you realize that your data set is not enough, is not covering enough. And so you might go back to the data collection and fix that. And so this whole process is very iterative. And then once you have something that you think you can use, you're going to be testing and deploying into production, and then you're going to monitor it for performance while the model is in production, so that if you see any problem, you can go back to the training or even to the data collection if you need to cover corner cases that you didn't think about. So this is a much more realistic, even if simplified workflow. And the enemies in this workflow are friction and chaos. So friction is what makes progressing in that workflow hard and unnecessarily so. That means things that take a lot of time, a lot of code, a lot of moving data back and forth, a lot of resources for things that can be automated and can be eliminated. So that's what I call friction. And then the other is chaos. The chaos is you get into chaos when you have a process that is unclear, is not documented sufficiently, and is not tracked and therefore not reproducible. And that means that even when you get good results, you cannot reconstruct what made the difference, what was that made your model make the jump in quality, for example. And that also means that collaboration is hard and onboarding new people is very difficult. And so these are the two enemies in this case. And so what is machine learning operations, or MLOps in short? So machine learning operations is a set of best practices and methods that allow you to have an efficient end-to-end development and operation of machine learning models that are performant, scalable, reliable, and automated, and reproducible, and is focused on a real production setting. So this is kind of my definition, at least, of MLOps. And so when you have, in a production scenario, if you don't have MLOps or you don't have sufficient MLOps, you might end up in the situation on the left. This is time allocation. And you could have like maybe 5% of the time of the project, you spend it on the problem definition. And then you spend the 50% of the time doing creation and cleaning and all of that. Then you have 10% of the time in modeling, 10% for the deployment, and 25% on orchestration. And that means creating configuration files, submitting jobs, getting results, trying to understand what happened, fixing problems, and all of these things that essentially are none of the other categories. Instead, if you have a good MLOps process, you might end up in the situation on the right. You still spend a lot of time in data creation and cleaning, that's unavoidable, but now you can spend 40% of your time on modeling, and you don't spend any of your time in the orchestration and deployment because those are automated for the most part. And so essentially MLOps is what allows you to focus on the real problem that you want to solve and not on all the corollaries and all of the infrastructure problems that you might have. Okay, so what I'm going to do in the next few minutes is to present these three levels of MLOps. This is a categorization that was first presented by the Google Cloud group in this blog post that I'm linking here. I took inspirations from that, and then I added a lot of things from my own experience. And so we start from level 0. Level 0 means that there is no MLOps. And this is typically what you start from everywhere. And so in this situation, the development target, so the final product of your development process, is a model. Maybe it's a pickle file, maybe it's an Onyx file, whatever thing you are doing, but your final product is the model itself. The code is pretty monolithic. It can be one notebook or many notebooks or many scripts, but it's not very reusable. And so refreshing this model is pretty difficult, especially if it's somebody else who wants to refresh it. You typically have little concern for production time, so you're just trying to make the best model without thinking at all about what will happen in production. And this usually also means that you have this situation of development and production asymmetry. So situations like, for example, there is a team that makes the model and then hand it off to another team, and this other team re-implements everything from scratch to fit into the production environment. This is asymmetry because what you use in development is not what is actually running in production. And this is very dangerous because the model could behave very differently for little differences, either in the code or in the procedure that you didn't realize. And then the deployment is pretty ad hoc. So maybe you deploy on a local server or on Binder or Heroku, and the process of the deployment is pretty ad hoc. It's very point and click and a lot of effort. And then typically you also have no monitoring. So you just deploy your model and then you hope for the best, essentially. You don't have any idea of what the model is doing in production. So this is kind of level 0. This is where everybody starts from. And indeed, this is what you typically use for side projects when you're focusing on something that is just a POC or a proof of concept or minimum viable product. If you want to study new techniques, in that case, production is not a concern. If you are building a proof of concept for your company, and again, production is not a concern, you just want to prove an idea, and then Kaggle competition. So an important thing that I want to say here is that level 0 is no MLOps, but it still has some applications, right? It's very important that we are balanced into how we apply machine learning operations. If you are in situations where you want to progress fast, you don't want to spend a lot of time in infrastructure, and if what you care about is not production, then you shouldn't. Probably this procedure here is perfectly fine. However, if you think that you might end up putting your model in production at some point, or you're sure that you're going to do it, then level 0 is definitely not the right level. And so you want to move to level 1. Before we describe what level 1 is, though, I need to introduce a concept that is one of the tenets of machine learning operations, which is the concept of pipelines. So what is a pipeline? A pipeline is a sequence of independent, reusable, and modular components that can be used to automate the machine learning workflow. So this is my definition. And so I show you here a pipeline. You have an input, I call it input 1, and then you have the first piece of software, component 1, that consumes input 1 and produces a product, an output that I call an artifact. And then this artifact becomes the input of the next step, and the next step produces a different output, which could be artifact 2. And then either one of the two or both artifacts become inputs of component 3, and then you get your final output artifact. So essentially, a pipeline is just a sequence of components that share inputs and outputs. And so if you are familiar with functional programming, essentially this is what it is. So you don't pass a state between the different components, you only pass inputs and outputs. Okay, so why are pipelines such a great idea? So by having independent components, you can have every component that runs on a different piece of hardware. So imagine that you are doing a deep learning model that needs to learn to train on GPU. GPU machines are very expensive. Before you get to the point where you're actually training, you probably need to do a lot of processing. For example, you need to download the images if you're doing computer vision, or you need to do expensive pre-processing and these type of things. So you don't want to keep your very expensive GPU machine busy with pre-processing that don't need the GPU just because, and then run the training on the GPU. It's much better if you run the step of pre-processing on a different machine that is optimized for that. Maybe it has a lot of GPU power, a lot of network bandwidth, and whatever you need for the pre-processing, and you reserve the GPU for the training of the model. And so you can have independent hardware for the different steps, and so you can choose the right hardware for the right step. And then independent components allow you to separate the dependencies and the versions. And so, for example, you can have a pre-processing step that depends on PyTorch version 0.5, and the training step that depends on PyTorch, the very latest version, 1.10. And these two can play together without any problem because they are completely independent from each other. They can have independent requirements. This is very important for the longevity of your company because of your component. Because if you build a pre-processing pipeline that works fine and there is nothing wrong with it, you don't need to update the packages in it, and you can use it until the end of times if you want, because the dependencies of that are stable, and you are not locking any other component to the same dependencies. And so this is very important for the longevity of your pipelines. You can even use independent languages in the different components. You can have pre-processing in Bash, maybe a script. You can do the training in Python, evaluation and plotting in R, and deployment in Scala if you want. Not sure this is a good idea, but if you want, you can do it. So it gives you a lot of freedom. And then the components are usable across pipelines. And so you can use them in many different ways, and you can just mix and match them as you need to achieve your results. Finally, the last two things are the transparency. So by having artifacts, input and output, you can always reproduce what went into a component and what came out of a component. And this is very important to understand what's happening inside your training. If you run into problems and you want to understand where this problem comes from, you can inspect these intermediate products and understand where the problem originated. And then this pipeline, and this is a monumental point, this pipeline can be triggered and run automatically. And this is going to be super important for continuous retraining, for ingestion, if it's a data pipeline, and so on and so forth. Okay, so this is an example of a training pipeline. This is a real machine learning pipeline. This is how a training could work. So you have your input data that comes into the fetch data component that saves the input data to maybe a file that I call raw data. Then you have the pre-processing that takes the raw data and cleans it and pre-process it however you need it and make the clean data. Then you have the data tests that make sure that the data is what you think it is. And these data checks are very important, especially when you run the pipeline automatically, because you want to make sure that the assumptions that you have baked into your modeling about the data are actually respected. So for example, if you think that a variable should have a certain range, you should test that that's the range. And that's what data checks are for. Then you have the train test splitting, train and test splitting. And so you have the training data and the test data. And then the training data gets into the training validation script that splits it again into training validation, does the training, the validation, the cross-validation, hyperparameter tuning, all the things that you want to do. And at the end of that, you have this inference artifact. This inference artifact is what I was referring to at the beginning by saying that a model should be deployable. An inference artifact is something that you can deploy. It's a form, it's a serialization of your model that you can actually put into a system and that system can use it to make inference. Then you have the test that happens after, because you want to test your inference artifact. So you test exactly what goes into production, and then you store your thing in the model registry. So this is an example of a training pipeline. Okay, all of this to say that now we can finally talk about level one. And level one is exactly the point, is you go from producing models to producing pipelines. So now the target, the deliverable of your project is not a model, but it's a pipeline. And it's the pipeline that can produce the model. And that means that this model can be reproduced at any time and can be retrained at any time on new data. And again, using pipeline gives you reusable components. You also want to track all the code that you use or the artifacts that produce and on the experiments that you do. And so you need the tracking. You can reach development production symmetry because the inference artifact that you have is exactly what you deploy. And so what you test in your pipeline, in your level one pipeline, is what you deploy. And then usually at level one, you also introduce monitoring production to make sure that the model keeps behaving as you want it to behave. And then usually also at this stage, you start having auto-scaling deployments like Kubernetes, ECS, that depending on the computing need of your model gives you more or less resources to compute your inference. Okay, so these are the key enhancements that level one allows you to reach. The first one is process standardization. Everybody is training models in the same way. That means that you can collaborate much more easily, and you can reuse things from one project to the next. You have rapid prototyping, because if you build a pipeline that can train, for example, a computer vision model that does classification, you can just change the input images and the output classes and retrain the exact same pipeline for a standard classification. And so you can create a prototype very, very quickly by reusing everything that you've done so up to that point. That means that you have a very fast go-to-market from when you have an idea to when you actually can deploy something that fulfill that idea. And you can avoid model drift. Model drift is what happens, or data drift is what happens when the data and input to your model change distribution as a function of time. For example, if you imagine what was the shopping behavior before COVID and the shopping behavior during COVID, there was a pretty drastic change. And so if you train the model to predict, your stock, the stock that you should keep in your warehouse based on a model that was trained before COVID, now your model is not going to work well after the beginning of the pandemic, right? Because there's been a dramatic data shift. And so you have to retrain that model on the new data to avoid this drift, to neutralize this drift. You can also use this thing to learn in production, which means you can build a feedback loop that retrain your model periodically, every day, every week, every month, to make sure that you stay up to date and that you train and you use all the new data that you have. And then again, by standardizing your process, you can have an easy handover. So there can be a person that does the version one of the model and then hand it over to a different person, and this other person will be able to pick up from there and continue easily. All right, so these were the enhancements of level one. There's also a level two, and the level two is this idea of continuous integration and continuous deployment. So now the development targets are not the pipelines themselves. The pipelines are pretty stable, but the components of the pipelines are the development target, which means that you can improve the components and retrain the pipelines with the new versions of the components. And so you have this continuous integration where every change in the components that passes some tests is merged automatically and becomes part of the production pipeline. And this production pipeline goes through continuous deployment, which means that every change that passes the tests is deployed to production. And then you have continuous training, which means every time either the pipeline change or you have new data, you can retrain automatically. And again, pending some tests, you release immediately the new model. And so this is a very, very automated way of dealing with things. And it's a very high level of automation. And this is level two. Okay, so the enhancements of level two are that you have rapid iteration on the production pipelines. You can do A/B testing every time you deploy. You can have very large teams working on the same pipelines because each team works on different components in different ways. and then your customers see continuous improvement because you can retrain very frequently in this kind of situation. Okay, so this is kind of a summary of the three levels. And so level 0 is you have the development target, your deliverable is the model. The retraining is difficult because everything is very manual. And this is a typical process for a team between, say, from 1 to 5 people, and you are at the proof of concept stage. So what you are doing is not really production ready. It's difficult to reuse. However, you need very little infrastructure, and the process itself is pretty easy. Level 1 is kind of it's a state transition. You go from developing models to developing pipelines. Retraining is much easier, and this is typically the process of a medium-sized machine learning team and a medium-sized company. And this is a production-ready and reusable process. And the infrastructure need is much larger than for level 0, but it's not impossible. And then you have level 2. Level 2 is typical of larger groups and larger corporations, and it's kind of the maximum level of machine learning operations, if you will. Okay, so let's look now that we did all of this to a realistic machine learning operations system with all the details. So we start from raw data that comes from vendors or our customers, and we store them in the raw form in an object storage like Amazon S3, if you know what I'm talking about. And then from there, you have ingestion pipelines that take this raw data set, transform it into the way that you need it, test the data to verify assumptions, and then ingest the data into, for example, in this case, a feature store. The ingestion pipeline itself is version controlled on GitHub because it's code. Okay, and then as soon as you have new data, you trigger a machine learning pipeline. So you make a data set, and then you feed this data set to the machine learning pipeline, for example, the machine learning pipeline that we looked at earlier. This machine learning pipeline is tracked. So the code is tracked in GitHub or in version control. And then the artifacts and the results of the experiments and all of that are tracked into the tracking system, which can be, for example, MLflow or weights and biases. And from there, you get your final training model that maybe it's a Docker container. In this case, it's a Docker container. And you save this model to a model registry. A model registry saves all the metadata, where this model came from, what was the pipeline run that generated this model, and all of that information. And then once you decide that your model is good enough, you promote your model to the staging stage, and this triggers a deployment. So a system takes your Docker container in this case, and it deploys it to a staging environment that could be, for example, Kubernetes. Kubernetes is a system that allows you to run containers in the cloud. This could be your staging environment. And from there, you do integration tests where you test that your model is behaving as expected, not only from the performance point of view, like accuracy, precision, recall, and those things, but also from the perspective of latency, throughput, and all of these other things. Assuming that passes, then you move to the production environment. So you have another deployment operation that moves your model to the production environment. And from there, customers can use it. And then you have your monitoring system that monitors that your model is keeps performing well. And if that system detects a drift, it can trigger that rerun your machine learning pipeline, retrain on new data, and kind of re-go through the whole process. So this is kind of a possible realistic machine learning operation system. So let's look at the people that are involved in this, because again, this is machine learning operations from the data scientist perspective, but it's important to understand what's around it. So this is the same pipeline that we just seen, the same system that we just seen. And the first part regarding data ingestion up until to the feature store or the data warehouse or wherever you're storing your data, that's typically the domain of the data engineer. And so, for example, your ingestion pipeline could run in Airflow or other systems like that, and it's typically the domain of data engineers. Of course, the domain of training models is the domain of the data scientists or the machine learning engineers. And so you essentially have the task of taking going from the data set to a trained model that can be deployed. But then both the staging and the production environment are typically the domain of the backend engineer, so a software engineer that is responsible for the backend of your product. And then everything else that you don't see within the colored squares, that's the domain of MLOps. And so the domain of MLOps engineer. And so the MLOps engineer needs to collaborate with a lot of people to build a system that can do all of these things and to essentially orchestrate the entire workflow. So every company has a slightly different way of approaching these things, but this thing that I'm presenting is a pretty typical kind of organization. All right, let me conclude my presentation with just a couple more slides about something a little bit different, which is if you've ever looked for MLOps or you've ever searched for MLOps, typically a lot of people present MLOps starting from this kind of quote, more than some scary percentage that can be 90% or 80% depending on the source. So more than, say, 80% of machine learning models never make it to production. Actually, the only source that I found for this quote is a report from Gartner, and the number there is 50%. So, but even then, I mean, it's more than half of the machine learning models never make it to production. So it's a lot. And typically what people say is that MLOps is the solution to this. Now, MLOps is definitely part of the solution, but I want to stress that it's not a silver bullet, right? There are many other things that go into a successful machine learning project. And so I want to briefly touch on this. So the first one is you have to solve the right problem, right? You want to solve a problem that stakeholders are interested in. You want to solve a problem that your customers actually care about. Otherwise, nobody would be very interested into deploying your model. You also have to have reasonable goals. So one typical thing that happens is that you overpromise with the magic of AI and machine learning, and then you underdeliver. You cannot reach what you promised. So it's very important that you have reasonable goals that you can actually achieve. And you can always do it better the second time, right? But the very first time, you should have very reasonable goals and conservative goals. You need enough good data because machine learning models are data hungry, and this is probably the most common cause for failure. You want to use machine learning because everybody does, but you don't have the data. And that's kind of a very big problem. So you really need to make sure that you have enough data of the good type. And then you also always have to expect that learning model is never made and done. You always have to expect that you're going to have to maintain it. You're going to have to make new versions. You're going to have to fix problems. The performance of your models are going to decay with time, and so on. So you always have to expect that there's going to be maintenance, and it's not only once you've done it, once you're done. And then again, you always have to be production focused so that whatever you decide, it's actually doable for your production environment. It's very typical to get a model that is very good in performance, but for one reason or another, simply cannot work in your production environment, and it, of course, is a showstopper. And then finally, you always have to expect that there is a very big team interplay, and I just show you how the whole system involves a lot of people and a lot of different profiles. And so you have to prepare for that, and you have to manage that, the team sport. Okay, so this is my last slide before my summary. Given the nature of the public here, I wanted to conclude with this type of diagram, because it's very easy to get confused about the different titles that are in this space. And so one thing that I find very useful to think about is kind of this diagram here, where you have these four corners that are analytics, machine learning, DevOps, and software. And then the different titles that you can see are in different places in this kind of diagram, and that kind of tells you the type of skills that you need to fulfill that role. So, for example, the analyst is, of course, very close to the analytics and very far from everything else. The data scientist is kind of in the middle between analytics and machine learning, and also a little bit closer to software and DevOps. So you definitely need to have good coding skills to be a data scientist. The MLOps engineer is much more on the DevOps and software side than it is on the machine learning side, but he definitely has knowledge about the machine learning and data science workflow and basic concepts. And then, I mean, you can look at yourself for the other roles. But I found that when you are looking for jobs on LinkedIn or on the other places, and you see these titles, it's good to try to place them also according to the job description into this kind of diagram and see if that's what you are interested in and what your skills are. Okay, so I'll here. This is the end of my presentation. Just a short summary. So machine learning in production is not the machine learning you do on Kaggle. Getting to a working model is only the beginning of the journey. MLOps is what makes developing real-world applications scalable, efficient, and standardized. And so it allows you to combat chaos and friction. There are 3 levels of MLOps, and we saw when you should apply the different levels. And then one of the main concepts of MLOps is the concept of pipelines. And so it's very important that you wrap your mind around it. And this will become essentially what you do. So the task of the data scientist will be to develop pipelines and not just models. Okay, thank you thanks again for having me, and I'll take any question you might have.
Wow, thank you, Giacomo. That was incredible. So much information, a lot there, and I think some very useful tips for people doing a Kaggle project all the way up to working in a huge company. And while we wait for some questions to roll in, I have a few of my own. So I know you mentioned that like a lot of companies already have these, like chaotic processes. Do you have any advice for people who might be starting their first job in a company that doesn't really have a good, pipeline structure and they're kind of diving into that chaos?
Yeah. So first of all, the first thing is not to get discouraged because everybody starts from there. Especially, I mean, I work in a startup, and if you work in a startup, especially a small startup, it's likely that you will find the situations like that, right? And so it's important that you you contribute to develop good practices within reason. Like you want to have a machine learning operations workflow that matches the stage of the company you're at. So if what you are at is you don't have any product whatsoever and you need absolutely to raise money because otherwise you die, you don't want to spend 6 months building your perfect level 2 machine learning operations system, right? That's not the right time. You want to have something reasonable. So there are reasonable things that you can do with very little effort, like tracking. You can do with very little effort. Definitely code version control you can do with very little effort. So definitely get everything you can that doesn't require a lot of effort, but don't worry about getting the whole thing immediately. Then once your company matures and your time increases, your team size increases, you get better and better, and you can introduce new practices and better tools and all of that match the stage of the company you're at.
Yeah.
Yeah.
Oh, go ahead. Sorry.
No, I just wanted to say it's important from the perspective of a data scientist. If you are the person who are driving the push towards a good MLOps situation, it's important to stay up to date with what's happening, and also it's important that you think very hard about building versus buying. Sometimes the best course of action for a company that doesn't have a lot of resources is to actually buy a product instead of building something from scratch, because building something from scratch requires a lot of time and then requires a lot of maintenance. You essentially have to have one or more people that are fully dedicated to that. So if you can, and that's very expensive as well. So it might be even more economical to buy a product than to buy it. If you are in a small company, if you are a company of 20,000 people, then you definitely have the resources to make your own, and it's probably worth it to make your own because you can customize it the way you want it.
Yeah, that makes a lot of sense. I think, on that point, there's a lot of great tools out there that people are already using in pipelines. Do you have any personal favorites or stuff you've worked with before?
So on the open source system, so the thing about the open source is that there are some kind of end-to-end platforms like ClearML is one of them, and there are others like Converge.io as a open source version of its system. These are end-to-end systems that can be worth looking at. If you instead want to build your own system based on open source, then you're going to have to piece together several different systems. And these systems, for example, for pipelines, a very common one is Kubeflow. Another one is MLflow. Just be careful when you venture in that you have to piece together a lot of pieces, and so you have to make sure that you have the resources to do that, and you have the knowledge to do that.
I'll jump in with a quick question. I know for depending on your the stage your company is at, right? Sometimes you might use there's a difference between like an enterprise level kind of tool, maybe to automate your ML pipelines versus something that might be more for a company that's at like stage 1 or stage 2. Is there like that kind of distinction in terms of tools you'd recommend for a company that's kind of just first getting started, starting to like build that capacity versus a company that's 10,000 people?
Yeah. So again, for a company that is just getting started, and it's also important to anticipate what the company will be like. If you're in a company that is going to use machine learning, maybe 2 or 3 times a year, 2 for 2 projects a year, and that's it. You definitely don't want to invest in building your own system. It doesn't make any sense, right? If you're a company that instead is going to grow to only do machine learning, 24/7, and that's what you actually sell, and that's your product, then you are in a different situation. So that's also an important kind of coordinate. But I would say for the very beginning, it's typically much easier to start from things that already exist.
Mm-hmm.
So I would typically think about end-to-end platforms for somebody at the very beginning, so that you can experiment with these things and understand the workflow without having to build it. You can use a platform intelligently so that you don't get a lot of vendor lock-in.
Mm-hmm.
For example, you definitely want all your code to be in GitHub, completely in your process, right? And you need to try to minimize the vendor lock-in that you get, but you can do that intelligently. And then once you have understood the workflow and you understood if the tool that you are using has things that don't fit your use case too much, or put constraints on what you can do and you don't like those constraints, then now you know what you want to build. You have a much better idea what you want to build, and then slowly you can go and build it. But in the meantime, your company can still create models and deploy them.
Yeah, absolutely.
Yeah.
Julia, do you have other questions?
Yeah, I was actually going to call out one from the chat that looked interesting. So Amamine asked if there's any platforms out there that automate the machine learning ops pipeline at level 1 or level 2. And maybe it'd be helpful to go back to those slides if you want to kind of refresh that, or yeah.
Yeah. So yeah, definitely. I mean, yeah. So maybe let's stay here more than level 1 and level 2. So so maybe this could potentially be a level 1 platform, a level 1 kind of situation, and there are definitely components. So I put some names in here, right? S3, GitHub, Docker, Kubernetes, right? I put here names so that you have a pointer to open source tools that do those things. And that's one way of doing it. You build your own thing, right? But there are tools that cover most of this. Like, for example, a lot of companies are using Databricks. Databricks, if you're doing classical machine learning, is a very standard solution that covers most of this workflow, if not all of this workflow. And that's of course not open source, but the open source part of that is MLflow, and MLflow is a tool that many people are using in the open source kind of environment. So yeah, definitely there are tools for level 2 and for level 1. There are either tools that cover little pieces of it, or tools that cover the entirety of it. Yeah.
Makes sense. And there's also another one that we got that looks interesting. Is there any specific resources that you use to stay up to date machine learning and new tools, or anything you'd recommend to people that are diving in?
Yeah, that's $1 million question. It's a very difficult problem because there's so much going on, right? So I would say from the data science and machine learning perspective, so research and best practices and things like that, I like to watch a few channels on YouTube that are very good. One is Machine Learning Street Talks, and then a few others. And then there's, like, for example, I am part of the Fast AI forum, where there are a lot of interesting discussions. And then I follow on Twitter the usual suspects like, Andrew Yang, Yan LeCun, and so on and so forth, right? So that you get what they are looking at, and you get a lot of nice resources. So I mean, there are these kind of resources, and depending on what you do and what you like, what you're interested in, you might find some of them useful, or some other. But I would say YouTube and Twitter are extremely good resources for this. On the MLOps side, there's a lot of things going on, and it's very, very hard to keep track of everything. However, one really nice resource that I like is mlops.community. It's a community of MLOps that is also has a Slack that you can subscribe to, and it's a very good resources. There are thousands of people in it, and you can get a lot of nice ideas in there.
That's great. Those very valuable resources there. Thank you for sharing that. And I wanted to touch back on something that you talked a little about earlier. You're talking about how there's really easy things like version control that you should just start from the beginning and make it right. But I was wondering about kind of evaluating processes and results, which I think is a little more difficult, but is actually really important to this whole process. To even know if you're improving your model through the work you're doing. Do you have any tips on kind of getting started with that for maybe startups who are trying to incorporate, an evaluation process in, or kind of best practices? Or
can you? I'm not sure I understood. So, can you maybe repeat the?
Oh yeah, sure. Evaluating the successful model, basically, kind of having checkpoints to make sure that you're actually the work you're doing is actually improving the model, whether it's new data streams or new processes.
Yep.
And I feel like that's really undervalued in a lot of these pipelines. That's crucial to understanding whether you're improving the system.
Yeah. So there's a lot to be said about that, and I was on the fence whether to touch upon it on the talk or not. But I had already way too many things, so I couldn't. But I'm glad you asked. So here on this slide, right, when you see tracking, right, it's extremely important that when you are developing a model. So there is an experimentation phase, right, which is what you want to achieve, you have the data, and now you have to find a way to get there, right? In this experimentation phase, you want to be fast, right? You want to be fast because you want to try a lot of things, but you want to be just like in a scientific experiment, you want to be very deliberate about how you try things. So you want to try one thing at a time and not many things at a time. Otherwise, you wouldn't know which one of them made a difference. And then you want to track all the experiments that you do so that you know what you tried, right? And then you can come back. Also, you can say, okay, let me try this. You try doing maybe using a certain architecture for a week and you go nowhere, right? And so you can come back to where you were and then start off in another direction, right? Because you track things. And now the next person will come along, will not waste another week trying the same thing that you tried, because we see your experiment, right? And we see what happened there. And so it's extremely important that you approach this in a scientific way where you track everything you do, which means you track the metrics, you track the code, and you track the artifacts, and you track the inputs, right? So if you want to reproduce a run, you need the same software, the same data, and the same hyperparameters. So you have to track these three things at the very least. And then through these experiments, you eventually converge to something that starts to work, right? And at the point you keep going into that direction, you do hyperparameter optimization, you do all of these things, and you zoom in on a successful solution. It's impossible for you to know that the solution that you found is the best possible solution ever, because you can never exhaust the space of all the possibilities. But that's not the point, right? In a production environment, what you need to have is a target. And once you hit that target, you should go with it. Just go with it, put it to production, start getting a value out of it. And you can always do a version 2 where you make it even better. There is no point in spending too much time trying to improve, because it's also diminishing return. At the beginning, you get a lot of improvement, and then the curve flattens out, right? And now you spend 3 weeks and you gain 0.5% in performance, right? And that's not worth it. So
yeah.
Yeah.
one more question if I could jump in. So I remember earlier you mentioned that you went through a boot camp. I know Julie did as well, and a few others in the call, of course. What would you say for people who are either going through that or thinking about it? There's only so much that they can possibly cover. Like in your experience, is there something that people should be like, in addition to going through your boot camp, like what probably isn't covered enough that maybe you should dive into or learn more about?
I mean, it really depends on the bootcamp, so I'm not sure I can answer for all of them. But I would say it's important that that you go a little deeper into what it means to put a model to use, right? So it's very easy to find resources that teach you how to build a model. And to be honest, these days, if you have good software skills and you have a minimal scientific background, you can learn how to build a model very easily, right? Because you have a lot of resources that are available to you for this specific problem. And there's also a huge effort that has been done by the open source community. So you have very, very nice tools that require very little intervention. There is even AutoML, right? So essentially, building the model is not the only thing, right? It's what you do with it. Like the difference is, okay, now that you have a model, how do you actually get value from it, and how do you actually use it for something that is useful? How do you make it robust so that it can actually work in a real situation, and all of these things. Now, it doesn't mean that you need to become an MLOps engineer, right? It doesn't mean that. However, you do need to understand how to make pipelines, how to track your things, what are technologies that allow you to deploy a model, and all of these things. So I would say after the bootcamp, if the bootcamp didn't touch on these things at all, that's maybe something that you might start from. Like, what is the difference between training a model in a notebook and actually putting a model out for thousands and thousands of people to use every day, 24/7?
That makes a lot of sense. Yeah. We'll take one last question before we wrap up here. And Scott asked one that is addressing how expectations with data science, like machine learning training, deployment, modeling, are kind of being more specialized, like that chart you showed where you kind of plotted these different roles. It'd also be great if you could pull up that chart maybe for visual reference. But so his question was, what is the future of the data scientist role?
Yeah, so yeah, definitely. I mean, roles are starting to become more specialized. That is definitely true. There's still, I mean, it also depends a lot on the type of company that you are going at. Like if you're going to a small company, it's likely that they need a generalist, right? And if you are in a small company, you also have to be ready to do more than just data science, because maybe in a small company they don't even have a data engineer. You have to do that work yourself. So sometimes these roles that I'm putting here it's actually always you that wear different hats and do the work of different people, right? So that I would say in a small environment, depending on the target, but typically the roles are more generalists. If you are in a very large company, roles tend to be much more specialized. You're gonna be one piece of a big machine, right? And depending on what you like and what your skills are, you might be a good fit for one or the other, and everything in between. But yeah, it's true that once you get to a mature kind of environment, things tend to be pretty specialized. For example, if you are in the deep learning space, there is a pretty big difference between a computer vision person and a NLP, natural language processing person, right? So it's true that many people specialize in one or the other, but it's also true that there are people that can do both, and there are situations where you have the possibility of doing both. So yeah, it's a very, very fluid situation. I think specialization is going to happen, but again, I don't think that companies that start from zero will necessarily have the need for a very specialized person.
That makes sense. All right, and we're going to wrap up on that note, but we'll have this talk available on YouTube. So if you want to go back, I know someone commented in the chat that they want to watch it again. So it'll be available for that. And Yeah, if you guys found this helpful, we'd love if you could leave a YouTube video or on our LinkedIn page, and we'll also help you stay on top of our future events, which we have some great ones coming up as well. But yeah, thank you so much, Giacomo. This has been incredible. There's been so many tips here, so many resources, and I know people are going to go back and review this and check out the things you shared. But yeah, that's it from us. So thank you everyone for coming. This has been a great session, and thank you for all your questions and all that. And yeah, have a great evening, everyone.